Another thing about using electron configurations, we can actually do an additional shorthand notation with it using something called the noble gas core configuration. So what we're going to do to write out the noble gas core configuration is we're going to look at the noble gas that's in the row above the element, write it in brackets, and then continue on with the electron configuration. For example, calcium, it's the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Well, if I go to the row above calcium, look at the noble gas there, it's argon, so I could just write argon 4s2. That argon in brackets, that represents the 1s2, 2s2, 2p6, 3s2, 3p6. Right? That's the electron configuration for argon, so rather than write it all out again, we just start with argon and add the additional electrons to get us to calcium. Could look at fluorine, 1s2, 2s2, 2p5, or I could write helium, 2s2, 2p5. Notice I didn't cut off the 2s2, I went to the noble gas, the line above it, started from there, and still wrote out the electron configuration beyond that point. Right? So helium is represented by the 1s2. Now with zirconium, it's actually going to be very beneficial. It's going to make writing out the electron configuration for zirconium a lot easier because I don't have to write out all of that stuff. I can just write brackets Kr, 5s2, 4d2. Brackets Kr represents everything from 1s up to the 4p. The other benefit of this, it's going to help us start to identify what our valence electrons are in these atoms. So things outside that noble gas core configuration are going to be valence electrons. Well, let's look at writing the noble gas core configuration from the periodic table. So here is my calcium. Right? I counted out electrons until I used up all my calcium. Well, all I'd need to do really now is I know where calcium's at. It's in row 4. Right? I'd go back to the noble gas and the line above it, start there. So I'd start with argon in brackets. Then I'd have to add 2 more electrons. Where are those electrons? Well, they're in the 4s orbital. So I'd write 4s2. All right, let's look at fluorine then. So with fluorine, it's number 9 there. So what I'd do is go back up. Helium would be the noble gas. And then I'd have to write helium in brackets, followed by, I'd still have to keep adding electrons, so I'd add the 2s2 and then the 2p5. All right, zirconium. Well, if I go to the row above zirconium, that's going to be the Kr. So the Kr is going to represent all those other electrons. So I write Kr in brackets, and then I have the 5s2 and the 4d2. Okay, so using noble gas core configuration, it's a much quicker way of writing out these electron configurations. But you need to make sure to pay attention. Is it asking for a noble gas core configuration, or do you want the complete electron configuration? Depending upon which way you're asked to write it, you need to write it the appropriate way. If you're not told to write it one way or the other, go with the noble gas core configuration. That's the quickest way to write it. Okay, so I mentioned briefly before the thing with valence electrons. All right, with valence electrons, those are going to be the electrons with the highest principal energy shell. Basically the highest N value. Everything below that is going to be something called core electrons. All right, so those are going to be the electrons in the lower energy shells. Okay, so with the calcium, all the electrons represented by that argon noble gas, so the 1s2, 2s2, 2p6, 3s2, 3p6, those are core electrons. The 4s2, those are valence electrons. All right, with the fluorine atom, helium, that's the 1s2, those are the core electrons, and then the 2s2, 2p5 are the valence electrons. So the number of valence electrons are going to affect chemical and physical behaviors of these atoms, and it's going to help us identify why calcium reacts one way while fluorine reacts a different way. Right, why does calcium form a +2 cation? Well, because it has 2 valence electrons and it wants to get rid of them. If it gets rid of those 2 valence electrons, it goes back to a noble gas core configuration. Fluorine, why does it become a -1 charge? Well, if fluorine picks up an extra electron, it goes to the 2s2, 2p6, which is another noble gas core configuration. Okay, so it's important to be able to identify these valence electrons and these core electrons. The valence electrons are really going to help us determine the behavior of atoms of an element. Okay, so elements in those same columns are going to have those similar properties because they have the same number of valence electrons in the same kind of orbitals. Right? If I look at the noble gases all have that S2p6. They all have 8 valence electrons. The reason why they're called noble gases is because they don't want to react with anything else. Why don't they want to react with anything else? Well, they're happy with the S2p6 configuration. Okay, that's a total of 8 valence electrons. And we're going to see later on that's going to be something called the octet rule. Things are going to try to get to this noble gas core configuration where they've got this S2p6 configuration, where they've got those 8 valence electrons. Okay, that's a stable state. They're happy with that. Now, the exception to this, helium is a 1s2. That's because helium can only have 2 electrons. It only has the 1s orbital there. Okay, so if we look at group 7a, the halogens, what ions do they form? They form -1 ions. Why? Well, if I add an electron to any one of these, they get to that S2p6 configuration. They reach that noble gas core configuration. So when looking at this periodic table, we can identify common ions based on the fact that they're trying to get to their noble gas core configuration. So if I look at sodium, it's in group 1. Sodium loses 1 electron. Where does it go? Well, it goes back to a neon configuration, right? Neutral atom of sodium has 11 electrons. If it loses 1, it goes back to 10 electrons. I'm back at neon. Everything's shooting for that noble gas core configuration. Okay? So when we write out electron configurations for simple ions, we're going to follow those same basic rules. Calcium atom has 20 electrons to start with. There's its electron configuration. The calcium ion that's going to be formed is calcium 2+. How many electrons does it have? It has 18 electrons. Well, if we write out the electron configuration starting with 18 electrons, we have the 1s2, 2s2, 2p6, 3s2, 3p6, which is that argon. So which electrons did we lose? In other words, which ones were the valence electrons? We lost the 4s electrons. All right, same way with fluorine. Fluorine starts with 9 electrons. There's its electron configuration. We form the fluorine ion, the F-. How many electrons do we have? We now have 10 electrons. So the electron configuration is now the 1s2, 2s2, 2p6, or the neon. Where did the added electron go? In other words, where were the valence electrons? Well, it went into that 2p orbital to get it to that 2p6. Right? That's where we added that extra electron. Okay, so keep this in mind. Why are elements going to form the ions that they do? They want to get to that noble gas core configuration. So noble gases have those 8 valence electrons. That's a stable state. It's very important that you recognize that. 8 valence electrons means we're stable. We don't want to give any more up. We don't want to gain any more. All right, we're happy with that S2p6 configuration. Except for helium. Helium can only get 2 electrons at most. All right, why can helium only get 2 electrons at most? Well, helium's in row 1. If n equals 1, L can only be 0, which means we can only have a 1s orbital. So we don't have any 1p orbitals that we can fill. So once we hit that 1s and fill it, we're done with row 1. Okay. So with that S2p6, noble gases don't want to react with anything, and that's for that stability of that S2p6, that octet rule, that 8 electrons. All right. If you look at the alkali metals, this is another example of this. They have 1 more electron than the previous noble gas. So which would be easier to do? Would it be easier to go from an S1, lose that 1 electron to go back to a noble gas, or would it be easier to go from an S1 to an S2p6? In other words, gain 7 electrons. Well, it's going to be easier to lose that 1 electron than it is to gain 7 electrons. Either way would get us to a noble gas, which is supposed to, in theory, be a more stable state. But in this case, the easier route is just losing that 1 electron. So they tend to lose their extra electron. They get back to the same electron configuration as a noble gas. And because of that, since they're losing 1 electron, they're going to form a cation with a +1 charge. Atoms and ions with the same number of electrons are going to be called isoelectronic. They basically have the same electron configuration. So if I look at my periodic table again, if I'm looking at this periodic table, let's say I have potassium. Potassium's in group 1. If it loses 1 electron, what's its electron configuration going to be? Well, it's going to be the same as argon. What about chlorine? Neutral chlorine is right next to argon. It's going to pick up one electron to get to that more stable state, so it'd form a Cl- to get it to that argon. Well, Cl- has 18 electrons. Potassium plus 1 has 18 electrons. Argon has 18 electrons. They would all have the same electron configuration. That's what makes them isoelectronic. Okay, they have the same number of electrons. Remember, though, they have different number of protons. That's what makes them different elements. But from the periodic table, that's where we get those general ions that are typically formed. Okay, we talked about that before. All right, another way to represent these electron configurations is going to be something called orbital diagrams. All right, so in orbital diagrams, we're going to use boxes to represent orbitals. We're going to use the up and down arrows to represent electrons in that orbital. So if I look at this orbital diagram, well, this orbital diagram is for what element? Well, I've got 1s2, 2s2, 2p4. Well, what has an electron configuration of 1s2, 2s2, 2p4? Well, if you look at your periodic table, that's going to take you to oxygen. So this is the orbital diagram for oxygen. Now, if we just look at the electron configuration as 1s2, 2s2, 2p4, we won't necessarily see that there should be two unpaired electrons for oxygen. We may just assume in that 2p subshell we have two pairs of electrons as opposed to one pair and then two single electrons. Okay, so the orbital diagrams are going to help us get a slightly better picture of how these electrons are going to be arranged within the atom. All right, now the importance of this in seeing whether we have paired electrons versus unpaired electrons is going to allow us to predict the property of something being paramagnetic versus diamagnetic. Something is paramagnetic, it's going to have unpaired electrons, and it's going to be attracted to a magnetic field. Something's diamagnetic, it's going to have no unpaired electrons, everything is going to be paired up, and it's not going to be attracted to a magnetic field. So just by knowing where those electrons are at, we can predict whether an element is going to be paramagnetic or diamagnetic. But with these orbital diagrams, we have to worry about Hund's rule. I mentioned this before. What Hund's rule is going to state is that each orbital in a sublevel is going to get one electron before any of them get two. Think in terms of pizza. All right, if a group of you get a pizza together, each person is going to get a slice of pizza before anybody grabs a second. At least that's how it is when my group of friends get pizza. Okay, so everybody gets a slice before anybody gets seconds. All right, that's Hund's rule. Okay, so let's look at this. All right, in particular, look at the 3p subshell and how it fills up in this table. So as we start to add electrons into the 3p, starting with aluminum, atomic number 13, we have an unpaired electron. Let's go to silicon, we have two unpaired electrons. Notice, I didn't put my second electron into the same box as the first one. Okay? Each one is going its own orbital before any of them get doubled up. Go to phosphorus, each box has its own electron. Once I hit sulfur, now I start to double up on those electrons. So the first box gets two electrons, followed by single electron, single electron. Okay, that's what Hund's rule is stating. All right, we need to be able to write these orbital diagrams from those electron configurations to better understand this. So let's just take fluorine, simple atom, we've been seeing it over and over again. Let's start writing orbital diagrams for fluorine. Well, I can start with my 1s2, so I've got an up arrow, down arrow, representing two electrons. The box represents that 1s orbital. I then move on to the 2s2. Single box, remember, s's only have one orbital. Right? I filled up that 2s orbital. Now I go into the 2p subshell. The 2p subshell is going to have three orbitals associated with it. Now I'd add one electron to each box before I start doubling up on those electrons. Okay? This would be the orbital diagram for a fluorine atom. Now, let's say I wanted to write quantum numbers for this. And let's say I wanted to write it for the third and eighth electrons that would be added into the fluorine. All right. Well, where's the third one going to be? Well, I'd start with my 1s, add those two electrons, so my third one would be that first electron in the 2s orbital. So in looking at this, if I want to write out my quantum numbers, remember, I write quantum numbers in parentheses n, l, m sub l, m sub s. So my n would be 2, my L would be 0 because I'm in the S subshell. M sub L would be 0. Got spin up, so my M sub S would be plus 1/2. All right, let's say I want to write the quantum numbers now for the 8th electron added. So where's the 8th one at? Remember, I go 1s2, 2s2, I've got 4 electrons there. When I hit that P subshell, each one of those boxes gets 1 electron before any of them get 2, so technically my 8th electron would be this one right here. Right, so I'd have 3 up arrows before I start adding my first down arrow. So what's the set of quantum numbers for that? Well, N equals 2, L equals 1 because we're dealing with the P subshell. M sub L is minus 1. Remember, M sub L is going to be negative L all the way up to positive L, so it could be negative 1, 0, plus 1. All right, that particular orbital I'm going to label as a negative 1, and then it's a spin down, so it would be a minus 1/2. Okay, so that's how I can get quantum numbers from those orbital diagrams. Right, so you need to be able to write orbital diagrams, you need to be able to pull out quantum numbers from orbital diagrams. What would the valence electrons here be? Well, they'd be the 2s electrons and the 2p5 electrons. For fluorine, when I add that extra electron, where's it going to go? Well, it's going to go to that 2p orbital on the far right, which only has a single electron in it. That's where that electron is going to go. Now, we are going to have some exceptions to Hund's rule. Right, and this is going to mainly involve the transition metals. Transition metals always cause some problems. When filling the orbital for transition metals, sometimes the n-1 d orbital gets preference over the ns orbital. What do I mean by that? Well, if I look at chromium and I were to write out the electron configuration for chromium, it should be argon 4s1 3d5. Using the methods we talked about previously, though, I should have gotten argon 4s2 3d4. Well, why does it half fill that 4s subshell and half fill the 3d subshell? Well, having a half-filled d subshell is going to be more stable than having a fully filled s subshell. So that s doesn't get its 2 electrons because it's more energetically favorable to have all the orbitals in the d subshell have at least 1 electron rather than have that s fully filled. Okay, where does that occur? Well, it occurs wherever we have what we should get, the s2d4. So if you look at that column that's got chromium, molybdenum, tungsten in it in the transition metals, all of those should be an s1d5 as opposed to an s2d4. Now, even then, there's going to be some exceptions. You can actually look in your book and see the actual electron configurations. In general, we want you to know these exceptions. The transition metals are always a little bit trickier to figure out. But if you go by the column that chromium's in and assume all those are going to be S1d5 instead of S2d4, it's going to be a pretty safe bet. The other column we have to look at is the column that contains copper. All right, copper is S1d10, not S2d9. Well, why is that? Well, similar to what we said previously, this time though, having a fully filled D sublevel is going to be more stable than having that fully filled S subshell. Okay, so it takes 1 electron away to get that fully filled D subshell. That's more stable. It's okay with having a half-filled S subshell as long as that D subshell is either half-filled or fully filled. So the elements in that copper column, the silver and gold, are going to typically be the S1d10 instead of the S2d9. When you look at the actual electron configurations for these, they're going to be slightly different. These are just general ways of predicting things. They're not going to be completely exact. Okay, you want to know the general basic ideas of how to predict these, though, using the periodic table. Another problem we have with transition metals in dealing with electron configurations is when we deal with their ions. Okay, now when we look at neutral transition metal atoms, we're going to fill the ns orbital before we fill the n-1 d orbital, except for those exceptions we just talked about. Right? Normally we go 4s2 3d something, okay, so that 4s gets filled prior to the 3d. But now when we form cations from these transition metals, we're going to remove electrons first from those s orbitals before we remove them from the d orbital. All right, so let's look at this. If I look at iron, neutral iron should be argon 4s2 3d6. According to what we were talking about before, the core electrons would be the argon, the 4s2 3d6 would be the valence electrons. Well, really, the valence electrons are going to be the electrons in the outermost shell. the one with the largest n value. So in this case, the one with the largest n value is the 4s. So when we go to form ions, those electrons get pulled away first. But this is only when dealing with transition metal cations. Okay, the other cations we talked about, those follow the rules of just wherever the outermost ones are, start taking electrons away. Transition metals, take it away from that 4s or that s orbital before the d orbitals. Okay, so if I form iron 2 plus, I lose those 4s2 electrons. If I go to iron 3 plus, that's when I lose one of those 3d electrons and end up with argon 3d5. If I go to manganese, that's argon 4s2, 3d5. If I go to manganese 2 plus, it's argon 3d5. If I go to manganese 7 plus, that's just argon. I've lost both the 4s and the 3d electrons. And manganese 7 plus is a stable ion of manganese. All right, but that's going to bring us to the end of writing out these electron configurations. We talked about writing out electron configurations, how they show us where electrons are at, what orbitals are in. Knowing what orbitals are in tell us a relative idea of their energy levels that they're in. We can write those for the neutral atoms. We can write them for the cations. We can write them for the anions. We can predict what cations are going to be formed because they're trying to get back to that noble gas core configuration. We can predict what anions are going to be formed. All that stuff comes from these electron configurations.